noticed my mic was off. Good afternoon, Rue. I'm doing pretty well. I'm excited that the weekend is upon us. How are you doing? It is a beautiful Friday. Rue, you're doing bad? What happened? Too many assignments coming up. Hey, just hang in there. One little bit at a time. We get one day at a time. Feeling great after that 451 test, am I right? Burge Lab this weekend. You guys do the Aero Lab on the weekends? What are you doing in the Aero Lab? Got some wind tunnel stuff going on, or the 339 lab is huge. Silent H, right? Burge ruined the weekend. He pulled a weather hold with that Aero Lab. What does it mean to pull a weather hold? Everyone procrastinated. He did not. This thing has been due for almost a month. Yeah. You know, no, that's the thing. Procrastination, I feel like that's... Some people are naturally good at taking care of things like as they come up. I have to work very hard not to procrastinate. So I'm definitely one of those people who's trying to learn not to procrastinate. But I feel you guys. It's not a... Man, time management is tough. I feel like it's a lifelong thing. COVID sync and non-sync work has been illuminating immense value. Wait, what do you mean by that? Expand. Are you saying that synchronous stuff has been more beneficial for you? Mega Mike, it's a hard skill to hone in on. Yeah, time management, that's no small thing. Like, yeah. The option to be non-sync forces you to plan. Oh, I see. Like if it's non-synchronous, there's less like structure and you have to make your own structure. I miss just walking around campus going to class. I miss that too. I miss seeing you guys just in the hallway or in the classroom or whatever. Yeah. I miss being on campus, seeing people. It was supposed to be your one chance to use the wind tunnel. Oh, you're not using the wind tunnel for the Aero Lab? Oh, I see. Thanks, COVID. Oh, that's a pain. Yeah. You don't get to do the lab in person, so you watch. Yeah. Oh, man. I know. I get the feeling that the season is changing without me noticing since I'm inside most of the time. Yeah. I try to get outside like a little bit every day. It makes a big difference for me to just like walk, see some leaves and stuff. Today feels like summer. It kind of does. It's bright outside. All the classes are online in the spring. I know. Yeah, it's kind of a bummer. Okay, we better get started here. I just want to blast this. Try to finish it by 3:50. Let's do this. You guys playing some frisbee later? Hey, that is a good way to spend your Friday afternoon. I'm glad you guys are doing that. Okay, guys. We've been talking about longitudinal flight dynamics. So those are dynamics about just flying straight as an arrow at a constant altitude. And it's the dynamics that happen in the neighborhood of that reference flight condition. So we derived a 4-dimensional model for that. And we looked at a 747. So we put some like real numbers in here to kind of get a physical intuition of what's going on. So we built a state space model, and a part of a state space model is the A matrix. And if you calculate the eigenvalues, we know from system dynamics that those eigenvalues, these are the roots of the characteristic equation for the system. And the characteristic equation tells you a lot about the system dynamics. It tells you about stability. It tells you if there is oscillations in the system. It tells you how quick the system is, like what's its settling time. And it also tells you important things like overshoot and rise time and other transient characteristics like that. So the type of routes we found for the Boeing, well, number one, they were stable. Thank God, right? How do you know if routes are stable? You look at the real part and you just make sure that the real part is negative. So these were the Boeing 747 routes. So these two pairs. And these have special designations. This one is the phugoid mode. And this one is the short period mode. And we're going to talk a little bit about physically what these modes look like today. I drew some fancy pictures, so we'll get to those. If you draw these routes in the complex plane, you're going to see the short period mode is kind of over here to the left. And we pointed out that that means faster settling time. If you excite the short period mode dynamics, they decay very quickly. For the Boeing 747, it's on the order of 10 seconds. These phugoid modes, they're slower. For the Boeing 747, so this is not as far to the left. It means that these dynamics are slower to decay. It takes around 1,200 seconds. What is that in minutes? I can't do that in my head. Are you kidding me? 20 minutes? 1,200 divided by 60? It takes 20 minutes. If you hit a gust of wind or something and there's no corrective action from the controller, 20 minutes for the fugoid mode to decay. All right, now the height of, or the distance from the roots from the real axis, which I'm just calling like a height in the complex plane, this is related, or this is the damped natural frequency, omega D. And that tells you the period of oscillation. So the larger the distance from the real axis, the higher the frequency is. So the short period mode, it has an oscillation period of like 7 or 8 seconds to complete a cycle. The fugoid mode, I think it takes about close to 100 seconds to complete a cycle, because it's much closer to that real axis. Let's break this down a little bit more. Okay. So like I said, relatively short period of oscillation. With a fast settling time. Let's just fill in some of these numbers here. So for the short period, for the 747, the damped natural frequency 0.9 radians per second. To get the period of oscillation, you take 2 pi, you divide it by that damped natural frequency, and we get about 7 seconds. And then the settling time, so that's the time it takes for these dynamics to decay, we have an approximation for that, which is 4 divided by the product of the damping ratio and the natural frequency, and that's about 10 seconds. So basically a short period, by the time it completes one cycle, the dynamics have already decayed, so you won't expect this to endure more than one cycle. All right. Let's talk about the fugoid mode, and then we're going to draw some pictures. We're going to draw some pictures. All right, the fugoid mode. Relatively long period of oscillation. Everything's relative, man. With a long settling time. All right, let's compare these for the Boeing 747. So the damped natural frequency, 0.07 radians per second approximately. And then to get the period of oscillation, so the time it takes to complete one cycle, 2 pi divided by omega D, and it's like 94 seconds. The settling time, we'll use that same formula from above. It's about 1206 seconds. All right, we've been talking about the period of oscillation, how long it takes to decay, but what does this actually look like? What is zeta again? Okay, so zeta is called the damping ratio. Called the damping ratio. Now, if something to remember, if zeta is less than 1, the system oscillates. I think that's the biggest thing to remember. You're going to have complex conjugate roots. So we already know, because these roots were both complex conjugate, the damping ratio should be less than 1. All right, how do we visualize these longitudinal flight modes? Let's talk about the fugoid first. Look at this beautiful picture I made. Okay. I think the best way to think of this is like a roller coaster. Because there's an exchange of kinetic and potential energy, just like there would be on a roller coaster that's following like a sinusoidal path like this. So, the aircraft follows a slowly decaying, so I mean in the case of the 747, it takes 1200 seconds, 20 minutes for this sinusoid to decay. Now if you look here, the longitudinal axis of the aircraft is always tangential to the flight path. So, because the body X basis vector is always aligned with the aircraft velocity, for the phugoid, the angle of attack alpha is always 0. The relative wind generated by our motion is always directed along the longitudinal direction. All right. But the pitch angle, so that's the angle of the nose relative to the horizontal. Theta is our pitch angle. Pitch angle is always changing. Remember, the pitch angle and the angle of attack mean different things. The angle of attack tells the angle of the relative wind, so it's something that has to do with velocity. But the pitch angle is about the orientation of the aircraft relative to the fixed frame. So that's why this pitch angle right in here, non-zero. Okay, the cool roller coaster effect of the phugoid is at the top. You're gonna have minimum aircraft velocity. I mean, it's definitely non-zero. We're moving like 700 feet per second, but it's going to deviate slightly from that nominal flight speed. So maybe at the top here, it's like 650 feet per second. I don't know. And then it gains speed as it goes down, as it gains kinetic energy. And then it loses speed as it approaches that crest again, and it goes back to like a minimum velocity. So I like this because this is like a pretty rich way of looking at this mode. Like you can kind of visualize what's going on. It's like a roller coaster. Okay. So pitch angle changing. And gains speed toward bottom. Loses speed. Let's just say it this way. As you're ascending, you're going to lose some speed. Gain speed, descending, loses speed, ascending. And the period is the time it takes to get back to the same place within the cycle. So this distance from here to here, or the length of time, that's the period, which is well, basically like 100 seconds. So it takes a little over a minute for a Boeing to complete this cycle. All right, let's talk about the short period mode. This one's different. Let's get this picture in here. Okay, so this is characterized by relatively rapid pitching about the CG. So that means like going nose up, nose down, that's a pitching motion. And when you pitch as you're oh, here we go. So you see the nose, let's say we're flying straight and there's like a gust of wind that kind of tips up the nose in an exaggerated fashion. Well, that'll excite this short period mode where we don't change altitude very much, but we move along at constant velocity, and the nose of the aircraft is just kind of like pitching up and down as we move in that direction. Now, because this constant velocity is just along this like straight line direction, the nose of the aircraft is changing relative to that velocity vector. And so in this case, if the velocity is always going that way, we do have an angle of attack. That's changing. Because it's the angle between the relative velocity and the nose of the aircraft. And in this case, the angle of attack, like if we're just flying totally horizontally, the angle of attack would be equal to the pitch angle. Because it just happens that the velocity vector is aligned with a fixed axis basis vector as well. So this leads to oscillations in alpha, the angle of attack. Unlike the phugoid, longitudinal speed is constant. The phugoid, it's kind of changing. It gets slower at the top, faster at the bottom. And another important feature is that the motion quickly damps out. So remember, the settling time is around 10 seconds, and the period of oscillation is around 7 seconds. So, and I kind of drew that here, that one cycle of motion would be, like I have the nose pitch up, and then so to complete a cycle would be the nose pitches up once again. But look at this, like the motion is kind of damping out, and the angle of attack is becoming like less and less. So all of that motion damps out after like one cycle. So the nose might pitch up, and then you won't really see much after that again. It's not like it's going to keep going back and forth and back and forth and back and forth. Okay. So that's kind of what they look like. So now we can visualize. Can you explain that again, why the angle of attack will be equal to the pitch angle? Okay, so the angle of attack is the angle between the nose of the aircraft, so this bx basis vector, and the relative wind. So if my velocity is going just straight horizontally, then the relative wind is hitting the aircraft like this. So the angle between the nose and the relative wind, that's alpha, okay? Now, what is the pitch angle? Well, I guess it depends on the definition of my fixed frame, but usually we'll have like fx horizontal, fz going down, and the pitch angle is the angle between the nose and the nose of the aircraft and that fixed frame basis vector. So if we have a situation where the velocity and this fixed basis vector are aligned, then in this case, the angle of attack and the pitch angle are the same. The reason they were different in the phugoid mode is because I was assuming that the velocity is always changing to follow tangential to this path. So in this case, the angle of attack is 0, but the pitch angle, if we still assume that that basis vector for the fixed frame is like aligned like this. You're welcome, my friend. Okay. All right, we're going to do some simplified models. So the way we derived the settling time, the natural frequency, whatever, is we took the eigenvalues of the A matrix, right? And that was a 4x4 matrix. Now, it turns out you can make a second order model for the phugoid and the short period that capture those same dynamics pretty well. And it's easier to work with the second order model than a fourth order model. So I want to show you these things. So for the phugoid mode, let's start with that. You can make a new set of dynamics. Now that we've visualized the phugoid mode, we know that it's characterized by changes in speed. Like it's slowest at the top, fastest at the bottom. So the speed is changing and the pitch angle is changing. So you can make a truncated model that focuses in on these variables. And let me just fill this in for you. This is our new A matrix for the phugoid. And it also has a B matrix, which we won't really use this today. We're just going to focus on the A matrix. But for the sake of being complete, we'll put this in here. So what I want to do is I want to use this simplified model, and I want to see if it predicts the same behavior that we know a Boeing 747 should have. And spoiler, this does a pretty good job. This is why we use this simplified model. And we're going to calculate the characteristic equation by hand. So the characteristic equation, if you have a state space model, it's this equation. The determinant of lambda times an identity matrix minus your system matrix. So if I substitute this in here, so I'm going to have lambda minus, okay, so I'm going to have lambda minus xu, because I'm subtracting the A matrix. And then this top right element minus g, if I subtract it, it's positive g. This is going to be positive zu over my nominal velocity. And I'm just subtracting 0 here, so I'll leave lambda in the bottom right. So if I take the determinant of this matrix, which is really easy to do, that's our characteristic equation. So just a reminder, the determinant is the product of this diagonal, and then you subtract the product of this diagonal. So I'm going to have lambda squared minus xu lambda minus the product of that other diagonal equals 0. Now, this is in a nice second order form where you might remember this from a dynamic systems class. This coefficient is equal to 2 times the damping ratio times the natural frequency. This coefficient is equal to the natural frequency squared. Just like that. So I have this relationship, and I have this relationship. All right. So that's pretty painless. Now I want to use these equations to compare results to the full model here. All right. Let's do this. So using this zeta omega n equation, that's equal to minus x sub u, so that's stability derivative divided by 2. I'm just getting that from the equation up above. And then I have a formula for the settling time. So the settling time of a system, the time it takes to decay, is 4 over the product of the damping ratio and the natural frequency. So if I substitute in this expression for that, I'm going to have the settling time is minus 8 over the xu stability derivative. And this stability derivative, we got it from a table in a textbook for the Boeing 747. So fortunately, for a lot of well-known aircraft, you can just look up these stability derivatives in a table. So let's get the settling time. So that stability derivative was minus 0.006868 seconds to the minus 1. And this is going to evaluate to 1,165 segundos. And this is compared to the 1,206 seconds that we estimated from the full model. So there's a little bit of error incurred there, but not too bad. All right. Let's continue here. So I have the natural frequency. If I use the expression up above, it's minus the gravitational acceleration times zu over my nominal velocity. So let's plug this stuff in. So gravitational acceleration minus 32.2 feet per second squared. This z sub u stability derivative is minus 0.08993 seconds to the minus 1. And then our nominal velocity was 774 feet per second, which I believe was like Mach 8 at 40,000 feet. So pretty close to the speed of sound. Okay, if you calculate all this out, this predicts a natural frequency of the phugoid mode, 0.06 radians per second. Now, to get the period of oscillation, so that's what I want to compare to. I know it should be around 100 seconds or so. I have to take 2 pi over the damped natural frequency, which is different than the natural frequency. It's not that much different. The relationship is the damped natural frequency is the natural frequency times the square root of 1 minus the damping ratio squared. So I need to calculate this so that I can substitute it in there. So I have the natural frequency, but I don't have the damping ratio. So we can get the damping ratio though. So the damping ratio, if we look up above, well, I know it would be minus xu over 2 omega n. And now I have this and I have this. So it's no problemo whatsoever. (0.0561). Now, if I substitute that into the damped natural frequency, I get 0.0611 radians per second, which, I mean, it's a negligible difference between the natural frequency. But that's only the case if you have a small damping ratio. Okay, so now we can get the period of oscillation, and it's 102.83 seconds. And this is compared to the 94 seconds that we predicted before. So it's a little bit off. Okay, so a question you might ask yourself is, okay, great. This simplified model gives relatively the same answer. There's a little bit of error. But what's really the advantage of using this simplified model? Like, is it a big deal to go from a fourth order model to a second order model? Like, can we not handle that? I think the important reason is that we have, using this simplified model, expressions, analytical expressions for natural frequency, for damping ratio, and it's connected back to physical quantities like the stability derivatives and the airspeed. So when we calculated the numbers before, we would not have had such a tidy expression for natural frequency and so on. So using these equations, you could say, all right, I want to adjust the period of oscillation of my phugoid mode for whatever reason. Like maybe you want to, maybe you're like, the settling time, it takes way too long. I want to back this down to like 900 seconds. Well, using this formula, you could say, okay, the settling time, it's basically related to this stability derivative, x sub u. And if I want to decrease my settling time, well, I have to make x sub u bigger. And in a previous lecture, we calculated another expression for x sub u. I can't remember it off the top of my head, but it was something like the dynamic pressure, plane form area, and then it was related to like the coefficient of drag and so on. And so this comes back to like maybe I need to change the area of the wing in some way, or maybe I need to change my airfoil so that this coefficient of drag changes. So what I'm trying to say is these simpler equations give you some kind of basic intuition of how do I actually need to play with the geometry of the aircraft to achieve some performance characteristic, like minimizing the settling time. So it's pretty cool. Okay, let's go on to the short period mode. We'll do this approximation, and I think we're going to wrap up right around 350. We're doing good on time today. Okay, so this is the second order model for the short period mode. This one, notice the parameters over here. Number one, we got the pitch rate. So Q is your pitch rate. And we know like this mode, it's kind of sending the nose up and down. So it's important that the pitch rate is in here. This is the speed, the velocity and the, well, it's the time derivative of the velocity component relative to the BZ vector going out the bottom of the aircraft. But think of this as related to the angle of attack. So it's basically describing, because we know that for this maneuver, our speed is held constant. So the angle of attack is the inverse tangent of delta W over U. So from this, we could calculate the angle of attack. Okay. Let's fill this in. So I got ZW in the top left element. I got the airspeed in the top right. And then I have these stability derivatives for the pitch rate. And I'm running out of room for this element. What I'll do is this. MQ plus MW dot. So that's our 2-2 element. And let's fill in this B matrix, even though we won't use it today. We're just going to focus on the A matrix. All right. So just like we did for the phugoid mode, we want to start by getting the characteristic equation of this. And I went ahead and just finished some of these lines because I think you get the process at this point. So I build this lambda minus A matrix. We got the A matrix up above. So you get this. The determinant is you take this product, which you see right here, and you subtract this product. So that's what we have right here. And then we just simplify it a little bit. So for one thing, you'll notice that these two terms are going to cancel out, like, well, when you consider these products on the outside as well. And you end up with this, where this coefficient in front of lambda, that's 2 times the damping ratio times the natural frequency. This is the natural frequency squared. And so what I want to do, I want to use these expressions. And let's see how some of the numbers compare to the full model. So let's start with the natural frequency this time. So natural frequency squared, it's going to be Z sub W, and I have a number for that. Minus 0.313 seconds to the minus 1. And then multiplied with M sub Q, minus 0.339 seconds to the minus 1. And then I have minus M sub W, minus 0.0011 foot to the minus 1 times second to the minus 1. And then that's multiplied with the nominal airspeed, 774 feet per second, which is Mach 8 at 40,000 feet, I believe. All right, when you multiply all this out, you get a natural frequency squared of 0.9575 1 over second squared. Or you could say it's radians over second squared. Radians is a dimensionless unit. So if we take the square root of this, we have a natural frequency of 0.9785 radians per second. So we're going to need this. Okay, let's get 2 zeta omega n. So we can see up here it's minus all these stability derivatives. I'm just going to give you the number for this one because it's just like we did for this one. We have numbers for those stability derivatives. We multiply them all out. So if you do that, you're going to get 0.7415 seconds to the minus 1. So now I can get the damping ratio because I know that the damping ratio is going to be this 0.7415 seconds divided by 2 times the natural frequency. And I have the natural frequency right up here. So I can sub that in. And you're going to get a damping ratio of 0.3789. Now this short period mode is much more damped than the fugoid. I think for the fugoid our damping ratio was like 0.05 or something. This is much more damping, which we expect. So now that we have the natural frequency and damping ratio, we can get the settling time. It's 4 over your damping ratio times your natural frequency. So we have the natural frequency, we have the damping ratio. If you multiply this out, you get 10.8 seconds. And this is a very good approximation because the settling time that we had before was 10.8 seconds. Okay, let's figure out the settling time. So, I mean the period of oscillation, my mistake. So the period of oscillation is 2 pi over the damped natural frequency. So that's 2 pi over your natural frequency times the square root of 1 minus your damping ratio squared, which is 2 pi over 0.9055 radians per second. And this comes out to 6.9 seconds to complete one oscillation cycle of the short period mode. And this is once again a very good approximation because the number we got before with the full model was 6.95 seconds. So just to drive this home once again, you can see from the numbers, these simplified models, they're decent for characterizing the basic dynamics of these 2 modes. Okay, so that's number 1. They're a good approximation. Then on top of that, they have the advantage that they give us some simple expressions that relate something like, now I have the natural frequency from this is the square root of these stability derivatives, which are related to physical parameters. So if I want to change my natural frequency, these formulas will give me tools as a designer to go back and say, okay, do I need to change my wing area? Do I need to change my coefficient of drag, coefficient of lift, so on and so forth? So it gives you power as a designer to make some general decisions about changes you want to make to your aircraft. So hopefully we can work in some examples like that in the near future, so you can see the true power, the unlimited power, as Palpatine would say. Is there a reason why the short period mode has better approximations over the fugoid mode? Good question. I don't have like a clean answer for that. Now, the way I can tell you this, the way that we arrive at these models in the first place is you take the fourth order model that we started with, you calculate the eigenvectors of that fourth order matrix. What those eigenvectors tell you is the relative participation of different perturbation states in those dynamics. Okay, so even though I say that, let's take the phugoid for example, that the angle of attack is always 0 or something like that. That's not entirely true. Like the angle of attack might be changing a little bit. It's just that the participation of the angle of attack in these dynamics is so small compared to the others that we neglect it. So that's kind of the price we pay with the simplification. So to answer your question, what I think is, when they did that eigenvector analysis and looked at how each perturbation state participates in each mode, maybe an assumption like this, just throwing out that angle of attack, it might have had a larger effect on this mode than some of the assumptions for the short period. That's the best I got. But I also expect that from aircraft to aircraft, some approximations might be better than others. I had fun making this picture though. That's one of my favorite things of preparing a lecture, trying to make a picture that says a lot of things. Like there's 4 or 5 details you can get out of a figure like that. So that's what I wanted to cover today. We're sliding in right around 350, and we did it. We didn't go over time. We just knocked it out of the park. So you guys are free to go play frisbee. Oh shoot, the sun is not as shiny as it was earlier. It's gotten a little overcast. Hey, have a good weekend, Billy. I hope you guys have a great evening, great weekend. Hope you get some rest. Hey, have a great weekend, Tim Srechtenwald. Thank you for always hanging out and participating. What's this song? Let me show you. This is called States Away by Sam Barsh. I threw it in the chat as well. This is what I use for the music on this channel. It's called Soundstripe. It gives you the license for the music, so we're Hey, have a nice weekend, Crispy Brownies. Have a nice weekend, Alden. Gives you the license for the music, so you're not in danger of copyright infringement. It's beautiful. It's always a pleasure to hang out with you guys and study flight dynamics. Thanks for your participation. Thanks for your questions. I hope you're enjoying it, because I am. Peace.